Hello. Today we're going to talk about two-plane bending. Now, in our previous video, we learned about normal bending stress, where if a beam is subjected to a coupled moment, that beam is going to bend. One side will stretch and be in tension, the other side will be in compression. And so we have a linear distribution of normal stress across this cross-section. Well, today we get a little bit more complicated. What if we take that same beam, but instead of applying just a single couple moment and having it bend in one direction, we apply two couple moments. And so that it not only bends, say, concave upward, but it also bends concave backwards. Each of the moments that's applied to the beam give a contribution to the normal stress that's applied to the beam. They also each give a contribution to how stress is distributed across the cross-section. Now, the stress itself can be calculated. The normal bending stress in the x direction can be calculated as follows, where it's equal to negative the moment about the z-axis times the distance y divided by the second moment of inertia about the z-axis plus the moment about y times the distance z divided by the second moment of inertia about the y-axis, where if we know our coordinates y and z on our cross-section, so if we know the location where we want to calculate stress, we input it and we find the value of normal bending stress anywhere on the cross-section, right? So fairly straightforward. Let's also note that in the form of this equation, we see we have a negative and a positive. This is assuming that the moments that we are applying are positive moments, meaning we are applying counterclockwise moments to our geometry. So again, if we know our y and our z coordinates, then we can calculate at any position on the cross-section what the value of that normal stress is. Now, the second moments of inertia. The second moments of inertia also need to be solved for. In terms of about the z-axis, it's the integral of y squared dA, and about the y-axis, it's the integral of z squared dA, where dA is something that we need to find, we need to solve for based on our geometry in order to actually integrate this equation here, right? So, and again, we'll look at some examples in class on how to actually solve these integrals. Let's also note that for the second moments of inertia, for simple geometry such as a rectangle, that appendix A18 has many of the closed form solutions to the second moments of inertia. So now that we've got an idea, this two-plane bending thing, let's actually try to visualize how stresses are distributed when we're bending around two directions. Let's first consider bending due to the moment about the z-axis. So the moment about the z-axis. In that case, we have stress that's linearly distributed, where at the bottom, we're in max tension across the cross-section, and on the top, we're in max compression, with a linear distribution going through zero at the centroid of our geometry, and then extending outwards, maximum out the outer edges, right? And this is the case where we're bending upwards, concave upwards. Now let's look at the moment about the y-axis. If we have a positive moment about the y-axis, we are going to actually be bending backwards, right? Where the front of our cross-section is in max tension, it decreases linearly through zero at the center, and then is in compression on the back wall, extending all the way down, right? So each of these separate give different contributions to how stress is distributed. Now, when we put them together, it's really complicated to draw. So instead, let's focus on finding where are the locations on our geometry if we consider both of these moments, both of these distributions, where is max tension found? Where is max compression found in combination due to both of these bending moments. And if we compare the diagrams and where they intersect, in combination, we'll find that we have maximum tension in the bottom corner and max compression at the top back corner, right? And so with these two plane bending problems, we actually have a bit of a more complex stress distribution across our diagram. Now, of course, if we've got our computer, we could just calculate what the normal stress is at every combination of position, but on an exam, we don't have that ability. So it's best to just think about the individual contributions, and then in combination, where is the max tension and max compression? Where are my critical points within my geometry? Now, two-plane bending in a circular cross-section is a little bit more complicated. In the case of a circular cross-section, we don't have, an edge that is consistently straight. And so often what we'll want to do is think of this almost as a vector problem, where if we have a moment about the z-axis and a moment about the y-axis, in combination, there is a moment vector where the moment is maximized. And perpendicular to that vector, we'll find max tension and max compression. We'll also be able to find an angle beta or also an angle alpha, which is the angle between our axes y and z and the position or the vector of the resultant moment, right? So we can move back to statics and summing those moments into a vector, right? Now, in our textbook, we've actually got a pretty long form equation for solving for what is the max stress for a circular cross section. In essence, it's the magnitude of the resultant moment times c, which is the radius of our cross section, over the second moment of inertia of the circular cross section. We can also kind of detail it out all the way to the point where we're putting in those individual contributions of the moment about y and the moment about z in our geometry. Key things to note is that resultant moment is simply the square root of each of the moments squared. So it's literally just the sum, the magnitude of each of those moments. And then that beta angle, the angle between the z-axis and the resultant moment, is the tan inverse of the moment y over the moment z, right? And with that said, that's pretty much what we need to know about two-plane bending. We need to know the equation. With the equation, if we know our y and z coordinates, we can calculate stress anywhere on the cross-section. If we want to know where overall we have max tension or compression, we can draw a diagram for each contribution of moment and then find the point where tension is magnified, where compression is magnified. And if we have a circular cross-section, we've got a little complex equation to play with, but if we can find the values, we can very easily solve for the normal bending stress. All right, catch you next time.